right, class. It's time to get started. Everyone bundle up. We're in for a ride today. Okay. I don't know what's going on here. I'll send another request. The first one, they said they fixed it, and it clearly was not fixed. Start a strike. Unfortunately, we have material to learn, so we cannot strike. No, we cannot strike. The work must go on. Frozen pipes be damned. All right, so I will send another request. I'll reach out to some more people, see what I can do about that. Because it's cold in here. It's warmer than it is outside, though, right? So so that's better. It's like 35. It's 52 in here. All right, so just one announcement about the homework. So homework 7 is due on Wednesday. I've had a couple of questions, and on Ed, there have been a couple of questions about how to get started. So all we've learned so far is laminar friction factor, right? Or at least by the time this was assigned. And at the start of the problem, you don't know whether or not the flow is laminar. So how do you get started? Well, you have to start someplace. So you have to make a guess, and then at the end of it, check that your guess was correct. In this case, that means guessing that the flow is laminar, because that's all we've covered so far. And then computing the problem as usual, and then at the end of it, checking whether or not the flow was in fact laminar flow, right? So check your Reynolds number, make sure the flow is actually laminar flow. We are going to see, as we solve turbulent flow problems, we're going to have some of the equations that we're using will be implicitly defined, as in you will have to guess and refine that guess and iterate to refine that guess as well. So guessing to get started is going to be a valid solution method here. And I saw your hand first, Jeff.
Yeah, so the homework, we need to do the guess and check for length.
So in the energy balance, yeah. So in the energy balance, remember we had the velocity terms, kinetic energy terms on either side dropping out, because V1 is equal to V2, right? But the velocity shows up in the friction factor, right? In the head loss due to friction, in the energy balance, right? You need to know velocity to know the head loss due to friction. And so you need to make some assumption about velocity and figure out the friction factor in order to get that head loss due to friction. So you do need velocity. And in this case, all you know is laminar, so it's reasonable to start with laminar. Okay, yeah. No, that's not true. So the question is, in the future, if you assume it's laminar and then you compute your answer, aren't you binding the problem to be laminar? No, what would happen if the flow were in fact turbulent, then what would happen is you would end up with a velocity that's high enough that you would be over the transitional Reynolds number. You'd be in the turbulent regime, right? So after you solve the problem, you would compute your Reynolds number. So when I say guess and check, in this case I mean guess laminar, compute the velocity, right? Or compute everything you need in order to figure out Reynolds number. Then check your Reynolds number and make sure that that your solution is in fact consistent with your initial guess that it was laminar. So if it were in fact turbulent, you'd end up with a velocity that's too high, right? That's above transitional Reynolds number. Yeah. Yeah, I mean, in this case, it's a good way to go, because laminar has a friction factor that is lower than the turbulent friction factor. And so, yeah, in that direction, it works. Now, in most real world cases, you're going to guess turbulence. Because in most real world, like pipe size flows, the flow is in fact turbulent. And we'll look at how we can, when we come back to the Moody chart, and we've dealt with surface roughness, likely on Wednesday of this week, we will talk about a good initial guess for turbulent flow that we can pull right off the Moody chart without actually doing any calculation, aside from looking at the roughness of the pipe. But again, you should check your Reynolds number. Whenever you're able to check the Reynolds number, you should definitely check it. Yeah, follow up. Yeah. So the question was, I'm just going to go back to a slide that has the Moody chart. When we do this, right? Initially, you're gonna solve the problem for now, right? Since all we know is this F is 64 over RE. So initially, you're gonna solve the problem assuming laminar, and then if the flow is in fact turbulent, you're gonna end up with a Reynolds number that's somewhere down here, as if you've or a flow where it's somehow down here, as if you've extended this line well beyond where it's actually applicable, and then you would know that that flow was in fact turbulent, and then you would have to go back and solve it using these methods. Okay. But guess and check, that's going to be a fact of life in this set of problems. Okay. Yes. It's a little more complicated. So the question is, if it's turbulent, you just read off the Moody chart. It's a little bit more complicated because it is a little bit implicitly defined. So depending on the type of problem that we're solving, and we'll see, we're going to split up turbulent flow in pipes into a couple of types of problems, depending on what we're trying to solve for. And so, for example, if we're trying to solve for velocity, you're going to have to do some iteration. So you're going to have to, again, guess, check your answer, and iterate and refine from there. Okay. All right. Any other questions? Okay. Okay, so we were talking about turbulent velocity fluctuations in the last class, right? So we had defined previously the Reynolds averaging operator. So U bar is 1 over some relevant time interval t, integral 0 to t of u dt. And this allows us, we said, to split the velocity into two components. The time average velocity, this U bar, plus the fluctuating component U prime, right? So this looks like this. So if this is our velocity U that we're measuring as a function of time, then, so the solid line is the velocity U that we're measuring as a function of time. U bar is just this time constant, right? This time average value. And then what's left over in that U is U prime. Right, what's left over, the fluctuations that are left over are U prime. The fluctuations around the mean are U prime. Yeah. So U prime is the time average velocity. So it can still be a function of space, right? But we're saying that it is, if t, for example, is the whole duration of our experiment or observation or something, then this U bar, is not a function of time. And U prime is a function of time as well as all the space variables, right? Okay, now one other property of this that we saw last time was that if we have some function A times some function B, and we multiply them together, and then take the time average, this is not equal to the time average of A times the time average of B. So a property of this definition is that we get this identity or non-identity. And so as a result of this, so if we apply this time averaging operator to Navier-Stokes, in this case to the momentum, this is the X momentum equation in Navier-Stokes, where we've applied that time average. We can see that we have a total derivative of the time average velocity, the derivative of the time average pressure, and we have time average velocities appearing here as well. But because of this property of the time average, we end up with these residual things that have to do with the fluctuating velocity components. These are non-zero in turbulent flow, okay? And we call these the turbulent stresses. And this is effectively, the problem that we have to deal with when we're modeling turbulence is how do we handle the turbulent stresses? This is what turbulence modeling is all about. And it's what the problem of dealing with turbulence and simulating turbulence is all about in fluid mechanics. So these things are turbulent stresses, and we call them turbulent stresses because they appear in a form that makes them look a little bit like the viscous stresses, right? So these terms here, these are our viscous stresses in the Navier-Stokes equations. And these turbulent stresses appear in the same place. And so they function in much the same way as the viscous stresses within the Navier-Stokes equations. So we call these the turbulent stresses. These are the impact of the turbulent fluctuations on the mean velocity field, right? Again, we want to solve for the mean velocity field. That's really the only thing we care about. Most of the time, that's all we care about. These terms here tell us about the influence of the turbulent velocity fluctuations on that mean velocity field. So we're going to start by looking at turbulent flow near walls and just talking a little bit about turbulent flow near walls. Because near a wall, we can actually model the effects of turbulence a little bit more easily. So we can handle the impact of those turbulent stresses just a little bit more easily. And we're going to get an answer here that actually comes out of a scaling analysis, is what's going to guide our work going forwards. So near a wall, we can model the effects of turbulence a little more easily. So we're going to consider we have some velocity u. So we're just going to consider a wall with, to start with, we're just going to say that there's no other wall on the other side. Okay, so we're just going to consider flow past a wall. We have some velocity u at some far distance away from the wall. In general, that velocity u can be a function of x, but we'll consider it to just be a constant for now. It's a constant uppercase u. And then we have this mean velocity. This pink profile is the mean velocity. Y is the coordinate that's pointing up in this case. And remember that the actual instantaneous velocity, what we would see if we instantaneously saw the velocity, that lowercase u is the mean velocity plus the fluctuating components, right? So there are many such traces, or a few such traces of potential instantaneous velocity profiles shown here, right? And what we care about though is what is this mean velocity profile u bar? Yeah. At every point, there are multiple correct answers. Yeah, over time, yeah, there are multiple possible answers. Yeah, and this is in stark contrast to the laminar flow case where there was one velocity profile, right? One of the things that makes turbulence challenging is that there are the instantaneous velocity profile varies, fluctuates. All of them are solutions to Navier-Stokes, right? So all of them are potentially valid solutions. But what we care about is the average velocity profile, the time average, and we'll see that we can actually get at least an approximation for that. So this mean flow is approximately in the x direction only. This is the x coordinate. It should be labeled as x coordinate. And just note for this discussion, we're interested only in the mean flow. So we're actually going to, for a lot of this analysis, be dropping the overbar. So on future slides, we're going to see u meaning the mean velocity u bar. Okay. And we're really just going to be talking about the mean flow from here. So if we look at this flow experimentally, it's generally thought of as having three different regions. Very close to the wall, we have the no slip condition, right? So the velocity slows down to 0 as we get very, very close to the wall. And that means you can think of like locally, like for the flow right here, very close to the wall. If the velocity is really low, like the Reynolds number gets really low, very close to the wall, like the local Reynolds number, like characteristic of the flow. And so close to the wall, the flow behaves as a viscous or as a viscous flow, as a viscous dominated flow as we get very, very close to the wall. And so very close to the wall, viscous effects. So even though we're looking at a case where this u, right, velocity is high enough that we have turbulence, when we look very, very close to the wall, the velocity is slow enough that viscous effects dominate. And therefore, we end up with a lot of viscous drag, a lot of viscous damping very close to the wall. We have an outer turbulent layer. This is the area that's further from the wall where we have full-on turbulence, right? So full-on, vortices creating other vortices and so on as we get further away from the wall. And then in the middle here, we have what's called the overlap layer, where there are some characteristics of the viscous dominated region and some characteristics of this momentum dominated turbulent region in this overlap layer. So this wall layer, this viscous wall layer, is less than 2% of this overall profile. So it's just a region. This is an exaggerated line here, but it'd really be like this tiny, tiny, tiny little region, very, very close to the wall, where viscosity is super dominant in this flow. So it's a tiny, tiny region of the overall flow. In the overlap layer, we have viscous stresses are important. Viscosity is important, but turbulence is also important in that overlap layer. And then in the outer layer, in this outer turbulent layer, that the viscous stresses in the Navier-Stokes equations are basically negligible, and the only thing that's the main influence we have to consider are the turbulent stresses, the impact of those turbulent velocity fluctuations on the flow. So in studying this flow, it's been found that that using a dimensional analysis, we can actually figure out what the velocity in the overlap layer needs to be. And this is based on basically experimental measurements of what's happening in the viscous layer, experimental measurements of what's happening in the outer turbulent layer, and then we'll actually see experimental measurements actually of this whole velocity profile. Led to a dimensional analysis, which led to this expression here. And this is telling us what the velocity in the overlap layer looks like. So u over u star, 1 over kappa, natural log of y, u star over nu plus b, where u star is tau wall, the shear stress at the wall, the square root of the shear stress at the wall divided by rho. This is like a non-dimensional form of the velocity u. Kappa has been found experimentally to be about 0.41, and b has been found experimentally to be about 5. So this describes the velocity in just the velocity profile, the shape of this thing in just this overlap layer here. Yeah. Nu here is kinematic viscosity. That's correct. This is kinematic viscosity. So what is this? If this is kinematic viscosity, what does this thing look like? Reynolds number. This is a Reynolds number. Okay. We're going to talk about this more in when we get to external flows, but this is just a preview of that. You'll notice that this length scale is a variable here. That's going to happen. We're going to be dealing with that quite a bit in next chapter. Yes. Do kappa and b ever vary? So for a flat plate velocity with just constant, sorry, for a flat plate with just constant velocity over it, no. But if that velocity starts varying, then the shape of this profile changes, and we would get different values here. Okay. But we'll actually look at some experimental data on the next slide, which will show that this is a good fit across multiple experimental conditions. Okay. Yep.
Works for any fluid and any surface.
Yeah, this fit should work for any fluid and a smooth surface. We haven't talked about roughness yet, and roughness is going to be important. But this works for any fluid and a smooth surface. That's correct. Yep.
So
Yeah. So and we're gonna extend this to a tube. Actually, on the next couple slides. we're going to say that, like, yeah, you'll see. We're going to extend this to a tube in the next couple slides and use this to find our velocity profile. Does the height of the overlap layer depend on the velocity of the fluid? Actually, the height of the overlap layer is going to depend on X. So the one characteristic we're going to see in so we've actually seen this in pipe flow. We talked about entrance length in pipe flow, right? So as we have flow into a pipe, the influence of the wall grows as we move into the pipe. That's basically like saying that this region where of this overlap layer grows as we move into the pipe. And so if we had a flat plate that's in external flow, so we have flow moving over this flat plate, that overlap layer region is going to grow and grow and grow as we move downstream, and just keep growing as we move downstream. I've exaggerated it. It would actually be like millimeters to a centimeter or something thick for a real flow, but it will grow and grow and grow and grow and grow. Within a pipe, though, remember the viscous influence of the wall. The influence of the wall grows until it meets the influence from the wall on the far side. So it stops growing at some point. Okay, so our dimensional analysis gave a result. This was our results from dimensional analysis, and it works pretty well. So this is data from, I'm like half laughing to myself because if one of my students in my lab came to me with experimental results that look like this, I'd say it worked better than pretty well. This is really, really good. So this is data for velocity U star versus they're calling it Y plus, but it's basically this Reynolds number based on Y, the coordinate away from the wall, from multiple different experimental measurements in some different flows. And we can see that, in fact, we have really good agreement, at least within this overlap layer, which is this region here. This velocity profile works really well, right? So everything lies along this solid line defined by the kappa of 0.41, B of 5.0, right in this region here. So within a pipe, this overlap region is pretty much the entire velocity profile that we care about. So when we have a pipe, we don't really have a far field region. We don't really have that far turbulent region. And the viscous sublayer, we said, was only like 2%. This is a log scale, right? So that viscous sublayer where we get deviation from this line is only about 2% of the velocity profile. In order to get into this like full turbulent only region, the region where turbulent stresses are the only thing that matter, we have to go really, really far away from the wall. And since we're confined inside of a pipe, we never have the opportunity to move that far away from the wall. So when we're looking at flow within pipes, this overlap layer is pretty much the only thing that it pretty much defines the entire velocity profile. So what we're going to try, or what has been tried here, is to just assume that this equation, which comes from scaling, of flow over flat plates, right? External flow over flat plates. We're going to say that we're going to take this velocity profile and say, well, what if we just make this velocity profile that we got, right, from this other type of flow, the entire velocity profile across the pipe. Like, this is probably what the velocity profile in turbulent flow looks like. But let's see how that works. And if we do this, we can get a semi-empirical solution to the turbulent velocity profile. So assuming the overlap layer equation works for the velocity profile across the pipe, we have U of R over U star is approximately 1 over kappa natural log of R minus R U star over nu plus B. It will look like this. So this is remember our laminar flow, we ended up with a parabolic curve. So for flowing around pipe, we have parabolic flow. Very similar to what we had for flow between two flat plates, right? Pressure driven flow between two flat plates, we've got a parabola as well. in turbulent flow, this form of velocity profile predicts something like this, which is indeed what we see experimentally, right? So we've seen some visualization of this, or at least the impact of this, right? When we looked at dye being released into different regions within the flow, it looked like it was being pretty well mixed across, which would indicate that there's a pretty flat velocity profile. And so this pretty closely matches what we see experimentally. One caveat here is that now that we're no longer looking at unconfined flow, so this kappa and B, we're going to have to deal with. They're not going to be 0.41 and 5 anymore. So we're going to have to figure out what this kappa and B are for this approximation to the velocity profile. Because now we have a curved surface, right, and it's confined. And we're just saying that this thing should approximately fit to what the velocity profile is. So we're going to have to do some more experimentation or look at some more experimental results, figure out what those things are. Yeah, sorry, when you asked if this fits for all flows, I was thinking of all external flows over a flat plate, like if we change the fluid. But now that we're using this as an approximation to internal flow, we're going to have to deal with these things again. Okay, so yeah, sorry for being a little misleading earlier. Okay, yes, Tata. Yeah. So big R is total radius of the pipe, right? So R is equal to 0 is at the center of the pipe. Big R is the wall, right, where we have no slip condition. R is equal to 0 is center of the pipe. Yep, that's correct. Okay. But if we have this velocity profile, we can get a turbulent friction factor, right? So just like we did for, remember for the laminar case, just going to go back. We said if we know the velocity profile, we can compute a whole bunch of things about the flow, right? We can compute the average velocity, right, by taking the integral of this velocity profile over the area and dividing by the area. Then we get the average velocity. We can do the same thing for turbulent flow, right, using this assumed velocity profile. We can get the friction factor, right? Because let's start with the wall stress tau W. We can get the shear stress at the wall by taking the derivative of this velocity profile and evaluating it at the wall, multiplying by the viscosity, right? Because we have a Newtonian fluid, we're assuming Newtonian fluid. And from those two things, we can plug into the definition of the friction factor and estimate what the friction factor is for, so we did this for laminar flow, right? And we had 64 over RE, right, is what we solved for. So we can do the same thing for our turbulent flow once we have this velocity profile. We don't really know, we have some fitting constants. This is why we say it's semi-empirical. We still have to do experiments. We'll have to do experiments to figure out what these things are. But we can find the friction factor as a function of these things first, and then measure that friction factor experimentally. So we can solve for the friction factor. So first we need the average velocity. So again, we're going to, so average velocity is Q over A. We can find that by, that's 1 over A times the integral of the velocity dA, right? dA is just 2 pi r dr. And so we'll get our velocity divided by that U star, our scaled, scaled effectively for velocity is going to have this form. Noting that V over U star, so U star is defined in terms of tau wall. So V over U star is just square root of 8 over F, the friction factor. We plug in our definition of friction factor. And so actually from this expression, we can solve for friction factor. And we'll get to that basically a Reynolds number based on that U star We expand that out. It's 1/2 Reynolds number based on diameter times F over 8 to the 1/2. And so our end result is going to look something like this. So square root of 1 over F is approximately some constant. So we've lumped together some of the kappas and b's and other constants that came out of integration. And so we have a C1 times the log of the Reynolds number based on diameter times square root of friction factor minus some C2. Right, so again, we said that we were going to have to find B and kappa again anyway for because we made some assumptions that this was going to work for internal flow. And so we've just lumped a bunch of those constants together into that C1 and C2 to make our job of finding these experimentally just a little bit easier. Yep. Yeah, and we've also rewritten it in log 10 because we like to deal with log 10 more often. So in this case, we're dealing with log 10. That's correct. Yep. Another question? Okay. Yeah, so we've rewritten it a little bit, right? So this this C1 then also contains a factor of like log 10 over log E, right? And so this is our predicted form. So we made an assumption of what the velocity profile for turbulent flow looks like. We carried through that assumption to figure out what the friction factor was. And now we're going to compare this to real data for real pipes. And we'll see some data on, we'll skip ahead. Well, we'll see some data on a slide, 2 slides from now. We'll see that it works pretty well. And in 1935, Prandtl measured pipe flow for a number of different Reynolds numbers, for a range of different Reynolds numbers, and he found that for smooth pipes, so if the pipe wall is pretty smooth, not very rough, and in turbulent flow, we end up with 1 over square root of F is about 2 log base 10 Reynolds number based on diameter, square root of F, minus 0.8. So for smooth pipes, this works pretty well. Okay. One thing I want to note here related to my discussion item at the beginning of class is that most of the time when we're solving a pipe flow problem, you want to know the friction factor, right? If we go all the way back to the beginning, we're going to, most of the time in this chapter, we're going to be doing an energy balance for pipe flow. We're going to look at energy in is equal to energy out plus frictional loss. That frictional loss, the head loss due to friction, depends upon the friction factor, right? And so if you remember, we're doing all of this, we spent all of this time discussing basically how to find the friction factor. And now we have, for turbulent flow, our first equation that we can use to find friction factor, right? So I could give you Reynolds number for a given flow and ask you to tell me what the friction factor is, right? So you want to solve for friction factor, you plug in your Reynolds number, but you also need your friction factor, right? So this is an implicit equation for F. So this is going to be another one of those guess and check kind of things, right? You're going to have to guess, if you want to use this, right? You have to, if we're going to use this, you have to guess some value of what your friction factor might be, plug in, and then iterate, right? You know, see what you get, see if it's consistent with the value of friction factor that comes out. If it's not, you're going to have to go through an iteration in order to figure out that friction factor. Okay. And we'll go through as we're solving pipe flow problems for turbulent flow. We'll talk a little bit about how to do that iteration. It generally converges very quickly, like 2 or 3 iteration loops. It will generally converge. It's the type of thing you can do by hand very easily. But yeah, but still, this is another guess and check kind of situation. And this is going to be a common feature of our turbulent pipe flow relations. There are many alternatives. So since 1935, right, many others have tried and come up with other solutions to this friction factor equation. And so there are many alternatives in the literature, you know, some of which are described within your text. This is sort of the canonical one that we're going to be basing our analysis on. So just a couple of notes about this turbulent pipe flow. So the again, the transition to turbulence is going to be at Reynolds number based on diameter of about 2,300. Right, experimentally, we can see transition to turbulence at certainly 1,800, Reynolds number of 1,800, and with perfect conditions, it can be extended up to many thousands. Right, Reynolds number of even up to 10,000. But typically around 2,300 is what we'll use as our typical transitional Reynolds number. The time average velocity profile for turbulent flow is very flat across the center and descends very steeply towards the walls, right? Drops sharply to zero at the wall. So in contrast to laminar flow, where we see this nice, smooth parabolic curve, right, for our velocity profile. In turbulent flow, it looks like almost all the fluid is moving at about the same velocity across the center of the pipe, with this really sharp drop to zero to meet the no slip condition at the wall. So it looks almost like a plug flow velocity condition. Almost like a uniform velocity condition, right, that we were assuming in our one-dimensional energy and momentum balances in chapter 3. Now notice that here we're talking about the time average velocity. There are still in turbulent flow significant fluctuations in instantaneous velocity, right? So if you were to sit here with a probe and measure velocity at this point within the pipe, right, just the x component of velocity at this point within the pipe, you would see values that are larger and smaller and larger and smaller and everything in between, right, over time. But on average, right, the time average would come out to this profile that we developed. So from our friction factor expression, if we plug everything in, we can find the pressure drop for a given flow rate for a smooth pipe as this thing here. Now we have all these weird powers, right? 1.75, 4.75, 3/4, 1/4. But the one thing I want to draw your attention to here is this dependence on pipe diameter. We have d to the minus 4.75. That's huge, okay? That is a huge power to be raising the diameter to. Okay, so what this is telling us is that diameter has a huge impact on pressure drop in turbulent flow. So if we have a pressure drop that's too large for a given pump, right? Let's say we're specifying piping that should go into some run within some plants, and the pressure drop that we're computing is too large for the given pump, right? That currently exists at the plant. And you're specifying this in stainless steel or something, so it's really expensive pipe. So you might be hesitant to specify, larger pipe diameter because the stainless steel is going to be pretty expensive. Well, you don't have to go that much larger, right, in diameter to have a really dramatic impact on the pressure drop. So just a slightly larger increase in pipe diameter can have a really dramatic, can really dramatically decrease the pressure drop across that run of pipe. So increased pipe size sharply reduces pressure drop in turbulent flow. Final note here on the smooth pipe flow section. So far we've been assuming that the walls of the pipe are smooth, but surface roughness does play a role in turbulent flow. In laminar flow, surface roughness doesn't really matter. Okay, it doesn't matter too much. But in turbulent flow, the roughness of the pipe, texture of the walls of the pipe plays a big role, and we have not discussed that so far. So that Prandtl relation is only for a smooth pipe with turbulent flow. Okay. So that's where we're gonna start talking about rough pipes now. Any questions on smooth pipes and turbulent flow? Yes. Yeah. So I think we have to talk about rough pipes before we understand what smooth pipes are in this case. And practically, we're going to say that a smooth pipe is one where it's going to get, my definition here is going to get a little circular. I was going to say a smooth pipe is one where the effects of roughness do not matter. We'll see on the actually there's data on the next slide, so let's look at that to guide this discussion. The effects of roughness was negligible in laminar flow, but turbulence does depend the shape of, or exactly what happens with this turbulent velocity profile depends quite a bit on what goes on within this viscous sublayer. So even though we assumed that because the viscous sublayer is less than 2% of the overall velocity profile, we said we were just going to ignore it, right? We said we were going to ignore it, and we just use the overlap layer velocity as our entire velocity profile. But what happens within that viscous sublayer is actually critically important for determining the final velocity of flow within the pipe. And because this viscous sublayer is so close to the wall, the effects of roughness are actually really dramatic on what happens to that viscous sublayer. So we do have to consider roughness when we're considering turbulent flow, okay, because of the influence of the viscous sublayer. So this is what real data looks like. So if we take friction factor, measured friction factor as a function of Reynolds number for a number of different pipe materials, right? Pipes of different roughnesses, pipes that are, fairly smooth all the way to pipes that are, really rough and pitted and rusty and awful looking, right? We'll see that within the laminar flow regime, right? So below Reynolds number of 2,000, 2,300 or so, all of the data falls on the same line, right? Which is that our Darcy friction factor 64 over RED, right? Everything falls on the same line. We get into this region here, where, what is this region? What's going on in this region? Transition, right? So this is the transition to turbulence. In this case, it's actually all pretty consistent. But you can certainly have this kind of jump from the laminar. So this is the turbulent relation. So you can have the jump from the laminar to turbulent relation happening at multiple different points along here, which is what makes this region so hard to predict. Okay, but this is the transition region, and then we have this line here, this dashed line. That's the turbulent friction factor for smooth pipe relation that we just developed on the previous slide. And then we can see, depending on the roughness, so these are epsilon, roughness of the wall, texture of the wall, height of the wall roughness, divided by pipe diameter. So for different values of epsilon over D, we can see the data diverges from this smooth pipe approximation at different points, okay? So this is where I was saying that we kind of have to understand, we have to talk a little bit about roughness before we understand what a smooth pipe is, right? Because for this value of epsilon over D, it actually behaves as a smooth pipe for a range of Reynolds numbers, okay? And as we increase Reynolds number, we eventually diverge from the smooth pipe expression, okay? So this is what real data looks like. So we obviously have to handle roughness. We have to understand something about the impact of roughness on the turbulent velocity profile, or the turbulent friction factor, at least, in order to handle real pipes. We can see that the deviation from smooth, when we're in the turbulent regime, deviation from the smooth equation, the Prandtl equation, depends on both the roughness, right, this epsilon over D, as well as the Reynolds number, right? So in general, higher roughness and higher Reynolds number cause us to diverge from the smooth approximation, right? Prandtl's equation. The other thing that we see here is that as we get to really high Reynolds number, right, all of these lines flatten out, right? So at high Reynolds number, the friction factor is actually no longer a function of Reynolds number. Right? So if we get to high enough Reynolds number, these lines are straight, meaning that they're not varying with Reynolds number anymore. And so at really high Reynolds number, the only thing that matters to figure out our friction factor is actually this epsilon over d, the roughness of the pipe. That's going to make it really handy when we have to make guesses for solving turbulent flow. So we're going to come back to the Moody chart. So for turbulent flow with roughness, this is an expression that works pretty well to capture all of that experimental data, like the data that we just looked at on the previous slide. So it's called the Colebrook formula or Colebrook equation, 1 over square root of f minus 2.0 log epsilon over d over 3.7 plus 2.51 over red square root of f. Again, notice that this is implicit in terms of f, right? F appears on both the left side and the right side inside of this logarithm. So there's going to be some guessing and checking that's required as we're solving problems, just like there is in the smooth pipe formula. The major difference is that some of these constants have changed, right? That we have that constant 2.51 there. It's a little bit different. And we now have roughness also contained within here. Okay. This is what's plotted on the Moody chart. So these lines here, okay, are the Colebrook equation. This bottom line here, that's Prandtl, right? But all of these other lines up here where we have roughness, these are all from Colebrook equation. This is our 64 over RE, right? Our laminar flow friction factor, okay? But that's where all of these different lines come from that Colebrook equation. There are some important limitations on this. So it's only accurate to about plus or minus 15%. Okay. You know, there are some regions where it's a little bit more accurate than others, but in general, only accurate to within about 15%. Okay, which is crazy. But this is, again, remember, we got here by making an approximation, you know, by assuming something about the velocity profile for turbulent flow from flat plate experiments that was measured in flat plate experiments. We extended that to what's happening inside of a pipe, got some constants that we fit to, and that was the Prandtl equation, right? And then we said, well, you know what? In real data, it actually also depends upon, the friction factor also depends upon roughness. And this Colebrook equation was basically like, well, it was basically developed by saying, well, it looks pretty good if I put it here. If I put my roughness in here, come up with some more constants and fit an experiment, you know, fit experimental data to it. So all of this comes from approximations that came from scaling analysis, approximations, and experimental fits. So it's a wonder it works as well as it does. And this 15% is good enough to do a lot of engineering work. Okay, you know, in actuality, you would account for the uncertainty in terms of a safety factor, right? If you have something that's safety critical. But so it's only accurate to plus or minus 15%. We're going to solve it by iteration. There's another form of the expression I want to make you aware of before we break for today, which is an explicit form, which has more error, but it's within about 2% of the Moody equation of the Colebrook, and so it's often, again, good enough. In this case, notice that F is on the left-hand side alone, and so this is no longer implicit definition. And so if you're plugging something into your calculator or into Python or MATLAB, if you still use that, then this is a good form to write out. Otherwise, we'll talk starting on Wednesday about how to solve problems by doing iteration.